Hello dear learners, welcome back to my YouTube channel. So today in this video we'll be doing a short derivation, and the topic for this derivation is electric field at a point due to a point charge. So here we will be obtaining the expression for the electric potential. Alright, so let's first understand the diagram. I'll explain you the diagram and then we'll do the derivation. So let's start the video. So here in this diagram you can see at this point O, we have a charge Q, and we are supposed to calculate the potential at this point P, which is at a distance of R from this charge Q. So we are finding the potential at the point P due to this charge Q, which is at a distance of R. And along the same straight line, we are taking other points. Here we have point A, which is at a distance of x from the charge Q, and at this point A, initially we are keeping another test charge, which is Q0, and this point here represents our infinity. So here we will be calculating, or we will be finding out the expression for the potential. So let's derive the equations. Now initially, when our test charge Q0 is at point A, then because of this charge Q at O, there will be some force exerted on the charge Q0, which is given by the Coulomb's law. So the force on charge Q0 at A due to the charge Q at O using Coulomb's law will be F is equals to 1 by 4 pi epsilon naught Q0 divided by x square. I hope you know the expression for the Coulomb's force. So it is given by F is equals to 1 by 4 pi epsilon naught Q1 Q2 divided by R square, where Q1 and Q2 are the two charges. So here the two charges are Q and Q0. Therefore we have written Q and Q0 here, and R here represents the distance. So initially this distance between the point A and O is x. So therefore we have written x square here. So following this equation, the expression for force on charge Q0 due to this charge Q at O will be F is equals to 1 by 4 pi epsilon naught Q0 divided by x squared. Now the direction of this force, since this charge is positive, this test charge is also positive, so the direction of this force will be along this side. A repulsive force will be exerted on the charge Q0, because we know positive repels positive. So this force will be along this direction. Now, if we bring this charge Q0 from point A to point B against this direction of the force through a small distance, let's say dx, and here we will consider dx as a vector because we are taking it from point A towards point B. So the displacement here is from point A towards point B, therefore we are writing it as a vector. So what we are saying here is, if we bring this charge Q0 from point A to point B against this force of repulsion, then a small amount of work has to be done against this force of repulsion. Now we know the expression for work done is W is equals to F dot ds, or F dot simply S, force dot displacement, it is the dot product, and when we expand this it becomes Fs cos of theta. So we will be using this expression here to find out the work done on charge Q0 when we take it from point A to point B through small distance dx. Since we are taking it through a small distance, work done will be dW, small work done, and that will be force dot displacement here is dx. So dW equals to F dot dx using this equation, since W is equals to F dot S. Now if we expand this, we can write this as F dx cos of theta here. Now let's find the value of theta from the diagram. So we have F dx cos of, now if you look at the angle between the force and the displacement dx, this theta is nothing but angle between force and dx. So force is directed towards right and displacement is directed towards left from the point A. That means these two vectors are opposite in direction, which means that the value of theta here will be 180 degree. So the small work done dW will be, so here if you put the value of cos theta 180 degree, which is -1, so cos of 180 degree is equals to -1. So small work done dW will become minus F dx. Let this be equation number 2. So what we have done so far, we have found out the force on charge Q0 due to Q, which will be repulsive force, again given by Coulomb's law. It will become F is equals to 1 by 4 pi epsilon naught Q, Q0 divided by x square. After that, what we are doing is, we are saying that if we take the charge Q0 from point A to point B against this force of repulsion, then there will be some work done, which will be dW is equals to F dot dx. If we expand this, since this is dot product, we have cos of theta. Now theta here is 180 degree, since F and dx, they are in opposite direction. So since the two vectors are in the opposite direction, theta is 180 degree. So cos of 180 degree is -1. So we are putting that value here. So -1 into f dx becomes minus f dx. So this is our equation number 2. Now, if our charge Q0 was initially at infinity instead of at A, if our charge Q0 was at infinity and we bring this charge Q0 from infinity to the point P, which is at a distance of r from the charge Q, then what will be the total amount of work done? That we need to calculate. So we can bring this charge Q0 from infinity up to the point P, bring the same amount of displacement each time. So displace it through distance dx, again dx, again dx. So each time you displace it through distance dx, the amount of work done will be dw each time. So in this way, we will come from point infinity to point P. So there will be a lot of work done dw here. So in order to find the total work done, all this work has to be added, or in simple terms, it has to be integrated. So in order to find the total work done here, we will integrate all the small amount of work done that is done on the charge Q0 when we bring it from infinity up to the point P. So let's calculate the total work done now. So the total work done on the charge while bringing it from infinity up to the point P will be integration. Why we are integrating? Because integration is simply addition of all the small amount of work done when we do it from infinity up to the point P. So integration, and we have a limit. We are bringing it from infinity up to the point P, which is at a distance of r. So from infinity up to the point r, whatever small amount of work has been done, that has to be added, and that will give us the total work done here. So therefore we have written total work done W is equals to infinity to r dW. Now from equation 2, we have the value of dW. This is dW is equals to minus f dx. So here we can write infinity up to r minus of f dx using equation number 2 here. So before we do the integration, let's put the value of f also from equation number 1. So W becomes, this minus can be taken outside, integration infinity to r. From equation number 1, the value of f is 1 by 4 pi epsilon naught q naught divided by x square, and we have this dx here. So here we have used equation number 1. Alright. Now before we integrate, we can see there is a constant term and a variable term. So whenever we have a constant and a variable while doing differentiation or integration, we always take out the constant outside the differentiation or integration. So here also we will do the same thing. So minus 1 by 4 pi epsilon naught, this is a constant term, so we can take it outside. Q naught is also constant, so we will write Q naught also outside the integration, and we have integration from infinity to r dx divided by x square. So here we need to integrate this term dx divided by x square. Now the formula for integration of dx by x square, you have to remember, which is minus 1 divided by x. So we will be using this formula of integration here. So when we integrate, this becomes minus 1 by 4 pi epsilon naught, q naught remains as it is. Now here, integration of dx divided by x square is nothing but minus 1 by x. And since this is definite type of integration, the limit is from infinity to r. So this upper one is called as the upper limit, and here this lower case is called as the lower limit. So integration dx by x square according to the formula is minus 1 by x, and we have the limit infinity to r. So next what we are going to do is we will replace the limit here. So before we do that, what we can do is this minus and this minus, if you multiply minus and minus, this becomes plus. So let's do that first. So minus minus becomes plus, and our expression becomes 1 by 4 pi epsilon naught q naught into 1 by x, and this is from infinity to r. So this minus has been multiplied with this minus and it becomes plus. So let's put the limit now. So when we put the limit, what we have to do is we always have to put the upper limit first and then minus the lower limit. So which means instead of x, first we will replace the upper limit, which is r, then minus, then the second one is the lower limit, which is infinity. So we have replaced the value of x, upper limit first minus the lower limit. Alright. So now here, if you see, we have two terms, 1 by r minus 1 by infinity. And here, 1 by infinity, you can take it as nearly equal to 0. 1 divided by a large number is nearly equal to 0. So this 1 by infinity, we can take it as 0 here. So then you can multiply this. So w will become 1 by 4 pi epsilon naught q into q naught divided by r. So let this be our equation number 3. So this equation number 3 is nothing but the total amount of work done on the charge q naught when we bring it from infinity up to the point P. So after we calculate the total work done, now we can obtain the expression for potential. So for that, you must know the definition of potential. So the definition of potential, it says that potential is nothing but the total amount of work done on a unit positive test charge, which means potential is work done per unit positive test charge. Now, if you put the value of W from equation number 3, then we will have V is equals to, in the numerator, 1 by 4 pi epsilon naught q naught divided by R whole divided by q naught. So this equation comes from the definition itself. So V potential is nothing but total work done by test charge. So we are replacing the value of W from equation number 3. So you can write down here using equation 3. Alright. So now here you can see that q naught and q naught can be cancelled. So our final expression for potential becomes V is equals to 1 by 4 pi epsilon naught q divided by R. So this expression V is equals to 1 by 4 pi epsilon naught q divided by R is the expression for the electric potential at a point due to a point charge. So in this way you can do the simple derivation. This is important one, so you can practice the derivation. Also you can practice numerical based on this equation. Alright, so do like, share and subscribe my channel, and please do watch the video completely so that you can understand, and share it with your friends. Thank you everyone.